Hi everyone, my name is Anna Deppenmeier and I'm a project scientist in the ocean section at NCAR. I'm excited to kick off the discussion on air sea observation networks and how they can help inform our modeling capabilities. Coupled global and regional climate models help us understand and predict weather and climate phenomena that affect people all over the globe. Due to the vast scales and the vastly different scales of our climate system, we can't expect to explicitly simulate all processes and therefore have to find adequate parameterizations. This is relevant in the ocean and the atmosphere individually, but especially at the interface, where heat, momentum, and biogeochemical tracers are exchanged. And I'm thinking specifically of the bulk surface flux parameterizations and the ocean mixing parameterizations that are vital for an interacting climate system. Both sets of parameterizations have come a long way, but our lack of long-term contemporaneous measurements still hamper our understanding and our ability to reliably model these important processes. We can illustrate the interplay of the surface and subsurface fluxes on the example of the tropical Pacific. Here in the eastern equatorial cold tongue, extremely large surface fluxes enter the ocean. These surface fluxes don't only enter the surface layer, but actually penetrate into the ocean interior, as can be illustrated by looking at the heat flux across the 21.5 degree isotherm. Together with these cold temperatures and large fluxes into the ocean and into the ocean interior are a long-standing problematic sea surface temperature biases and actually also subsurface biases. So here on the left-hand side, I'm showing you a rare set of observations of subsurface turbulent heat flux measurements and surface flux measurements indicated by the little stripes on the top of the panels. And you can see that if you compare the measured turbulent fluxes to the modeled turbulent fluxes on the right, the model vastly overestimates the heat that is taken up into the ocean. And I can tell you that this goes together with the warm subsurface temperature bias. So this is a rare example of how direct turbulence measurements can help us guide model development and process parameterizations, and we need more of these observations. Recently, we have used a high resolution global ocean model to investigate the diabetic part of the circulation. This diabetic part of the circulation means that water is being transformed from, for example, colder to warmer temperature classes, and this is mostly induced by turbulent heat fluxes. But those heat fluxes, as we've just seen, are biased. So we really need vertically resolved turbulent heat flux measurements so that we can understand how these fluxes influence the diabetic circulation in the real world. And we don't only need those observations at a single space, but we need them spatially resolved so that we can understand the spatial imprints of the diabetic circulation. In the long-term mean, as you can see here, the diabetic circulation is fairly homogeneous and tightly focused on the equator. But if you look at shorter timescales, there's actually considerable spatial variability that we need to understand. This spatial variability of this diabetic upwelling and the turbulent heat fluxes goes together with as an imprint of the surface heat flux and the sea surface temperature imprint. And again, this highlights the need for collocated surface and subsurface measurements to understand the interaction between the surface and the subsurface in the real world. Summarizing, we need contemporaneous surface and subsurface measurements in a network and over a sustained period of time to capture spatial and temporal variability. And we should be thinking about autonomous vehicles, remote sensing, and supersites to really understand how the ocean and the atmosphere interact. Thank you.